So I'll try to explain this code. So here the main tool I use is JAX, and this is a library to do array computations like NumPy, but faster and with extra nice tools to compute derivatives and other transformation functions that are very nice, like to parallelize the code. But I'm not sure I'm using much those tools here. Maybe through Diffrax, because Diffrax is a library built on top of JAX to do integration of ordinary differential equation using the usual algorithm like Runge-Kutta. This it 5 is just a special case of Runge-Kutta. So yeah, this is the main tool I need. This Equinox is just it's a library made by the same guy that made Diffrax. It's made to make objects that contains arrays of the JAX ecosystem. It's just a kind of an utilitarian library to manipulate JAX arrays in a more like object-oriented way. So this goes together well with this. And this is matplotlib to plot stuff. Just use it at the end. Is NumPy. I don't know where I use it, but very common library. Then I do the computation in Float64 to be precise. I don't really know if I need it, but always good to start with that. And then I try to separate a little bit the when you try to integrate something, you need to discretize the space and use a like discrete way to compute the derivatives, and I try to put all this discretization strategy in this class. And what I realized I need is I need a grid, 1D grid. So by the way, I'm just solving Maxwell equation in 1D. I'm assuming all my fields are constant along y and z directions and only vary along the x direction. This simplifies a lot the Maxwell equations. I will place some charges. The charge can move in x, y, and z direction, if I remember well, but they are also constant charges along y and z. So think of them as big planes of some charge. Planes of charge, and these planes can move along the z direction, obviously, but the plane can also have a velocity along the two other directions, y and z. So when I do discretization, I need the step, discretization step. I need, given a field, which is a 1D array of discretized value of this field, I need sometimes to evaluate this field at some value x. I just do simple interpolation. This is a GNP is from JAX. but it mimics the NumPy API. So if you are used to NumPy, it is the same behavior as np-interp. Then dx is given a field again. A field is just a 1D array of same shape as the grid. Given a field, compute its derivative. For that, I just take the field, shift it by one, the entries, shift the entries by one in one direction, shift them in the other direction, compute the difference, and divide by 2 times the step. And this function is also useful. Dirac, given a position somewhere, discretize what would be a Dirac delta. If x is exactly on a grid point, I think it will be just something like 1 there and no, actually not 1 over delta here and 0 everywhere else. The idea is that you want this thing to be as localized as possible. You also want it to be integrated to 1, but still behave a little bit smoothly when you are in between 2 discrete point grids. We can plot this to see how it behaves, by the way. So if I execute this, you can see if I take this cell, let's put it below the cell we already looked at. So now if I do sim.delta, so here I have the number of discrete point space in the space, x minimum, x maximum. So if I put some value, 0.1, it's in the range. What did I do? Delta is it's Dirac. Of course. Maybe I can remove this thing, or just do that as array. Okay. If I plot this, it's a Dirac delta. And if I zoom in, oh, I missed it. Oh yes. Sim.x grid for the x-axis, maybe it's better. 1.5, 0.8. We can put some dots. You can see it's not, since this one is not falling exactly on a grid point. Well, it's hard to get there, but it's not falling exactly on a grid point, so the Dirac delta is made of 2 non-zero values along the grid. Okay, so now I need to have quantities to represent the state at some time, at some given time. For this I have this class for the charge, for one charge, and then I have many charges, many of these guys. a charge is made of a position. If I remember well, it has like xyz position, xyz velocity, a scalar for the mass, a scalar for the charge, an anchor and an omega. This is because in my model, the charges are, these planes are anchored at some point, and they behave as a harmonic oscillator. So they can if we pull them away from the anchor, there's a force that pull them back to the anchor, and this is the to parameterize this force. And so the whole world is parameterized as many charges. I will use this thing I very briefly mentioned of Jax to be able to parallelize things. So it's called VMAP. So this will contain actually many charges. It's of the type charge, but it will have actually contains more than one charge. Then the electric field along x is actually 0. Oh, it's actually not 0. It can be any value, but I set it to 0. Same for a magnetic field in the direction of x is also a constant that I also set to 0. This is to evaluate the value of the electric field at some position x. What is Ex? Ah, yes. Yes. So electric field along x is not a constant. It depends on the position of the charge. Every time you pass a charge, the electric field raises if the charge is positive. And so this is here. You look where you are. You do minus the position of the charges. You multiply by the charge of each charge. This is executed in parallel thanks to VMAP along all the charges, and you sum everything. So if you are left or right of each of the charge, you will get a contribution amount. So this is for Ex, and Ey and Ez is just evaluated using this dot at I showed before. For B it's the same, but it's 0 in X. And now the current is only determined by the velocity of the charges and is 0 everywhere except if you are on the charge, and that's where we need this Dirac delta. And again we execute this in parallel over all the charges, and the sum is to sum all the charge together. So we get the output of this, if I remember well, is a one-dimensional array with some Dirac deltas, positive or negative, depending on the actually I don't know, actually it is a it's a vector field, so it's probably shape NX3. Thanks ChatGPT. So yeah, it has 3 components, and dot is the derivative of every single entries, so to be able to integrate everything. So the derivative of the fields, electric and magnetic field, are given by the derivative of the fields themselves plus a contribution from the current, and the derivative of the charges, mass and charge do not change over time. Position is simply the velocity, but the velocity is there's one contribution from the electric field and magnetic field, and another contribution from the harmonic oscillator. So position minus anchor and some coefficient here. The anchor also 0, the derivative, time derivative of the anchor is 0, time derivative of omega is 0. We can execute this cell. Okay. And now we need to initialize the world. This is an envelope function to initialize some wave that is localized. I use some just an exponential, a Gaussian, just a Gaussian envelope. So I have the envelope, I have some sine function. So it will look like that. This is my initial wave. This is a function to initialize the charge. This is the mass of the charge. Position, initial position, velocity 0 at initialization. Some anchor is at the position at initialization. And here is where I initialize the charges. I alternate the charge -1, 1, -1, 1 to make the whole system neutral. And I put many charge between 10 and 15 along my axis. What's that? Oh, I guess what do I do here? Repeat. Maybe I place repeat. Not sure. Maybe I place a positive and a negative charge on top of each other and so on. In EY I put this wave, and in BZ as well, 0 for the two others. And then I evolve this for some time, and these are the time steps to visualize the evolution. And this takes some time to do the Runge-Kutta integration. So this is taking the initial state here, and this function gives the derivative of the state, integrated with Runge-Kutta until the end. This is the initial time step, but there is a step size controller using a PID that is trying to achieve some error, and it's saving also along a grid in time. It's saving the states. So this is done. So now I can just plot. So here I have a figure. I'm showing the electric field along the y direction. And I'm also showing the trajectories of the charges along the x direction. So this is the x direction, my grid. This is also my time grid. You can see the charges They are, at the beginning they don't move, and then they start to oscillate a little bit. Looks like this one oscillate more than this one on the left. On the left they oscillate more than the charge on the right. This is the wave packet that arrives. Some get reflected, and I've put this green line. The green line is just a straight line that goes at the speed of light, and so we can see that the light is slowing down, and then it exits and go again at the same speed. So we can see light slowing down because of the presence of these charges.